everybody, wherever you're joining us from around the world. My name is Andy Purvis. I'm Director Sustainable Manufacturing with the World Steel Association. I am delighted to be opening the second of a series of webinars we are running throughout this year, focused on issues around gassing and asphyxiation. And we've selected this as a topic because this is really one of the critical risks, and I think the causes of a high cause of fatal incidents and serious injuries across our industry. And I'm absolutely delighted again to be partnering with the team from Draeger, the renowned global international industrial gas company, who are going to talk us through our webinar today, which is focused on explosive gas atmospheres, how we can take preventative measures, and gas warning devices that may be available to protect us. We intend to go for around an hour. If you have any questions that occur to you as we go through the presentation, please feel free to ask them. There is a Q&A function at the bottom of your webinar page. Type them in there, and we will address as many as we can at the end of the presentation. It's better to use Q&A rather than chat, because chat is wiped at the end of the webinar, whereas the Q&A can be preserved, which it'd be good for us to do. On that note, I will terminate my introduction and hand over to Team Draeger. Oliver, the floor is very much yours. So thank you, and over you go.
Thank you, Andrew, for this warm welcome, and hello, everybody. Thanks to all of you for joining today our webinar sessions, and I am very convinced that there will be some valuable insights today for you that we prepared. So the last sessions, the first session we recorded by end of April, we had a focus on the risk assessment. So the first step to have a holistic safety concept. Today we will have a deeper dive into a more detailed topic, and that's a bit about explosive atmospheres, the risk resulting out of it, and of course the preventive measures and the technology we can use. So very warm welcome. And for those of you who expected to meet my colleague Friederike today, I have to disappoint you. So Friederike won't join today due to illness. So she lost her voice nearly completely. So yeah, it's up to me, but I'm optimistic that I will fill the gap today. At least I will do my very, very best. And luckily, I am not alone on the stage. So Markus is with me, and Markus is our expert on explosive atmospheres at Draeger. So Markus, just a few words about you.
Thank you. Yeah, my name is Markus Oertel. I'm with Draeger more than 10 years, all the time in the what we call the fixed gas detection department, means looking to technologies to detect and to measure toxic gases, oxygen, but also explosive gases and vapors. And my role is a product manager, and I'm dealing with sensor technologies, especially electrochemical and catalytic bead, which will be part of my presentation today.
Yes, thank you,
Welcome.
Markus. Good to have you here. And before we come to the first content part, I would like to introduce very briefly Draeger as a company, for those of you who don't know us yet. So Draeger is a family-run company in the 5th generation. We are located, the headquarters is located in the north of Germany, in Lübeck, a very beautiful town near to the Baltic Sea. So we have about 16,000 employees with a net sales of a bit more than 3 billion euros. Yes, we are located in Germany, but you will find all our subsidiary all around the world. some details you will see here. So there are different production sites, logistics centers, and sales and service locations, and one of them might be also quite near to you. Yes, so I would suppose let's start. Let's start with the topic. And we prepared 3 chapters, so to say, for today. And I would like to give you a short introduction with a focus on the transition phase the steel industry is currently in. Then we will go on with Marcus and some insights about explosive atmospheres, and then we come back in the end to a short best practice from one of our steel customers. Okay, so let's start. The transformation of the steel industry. So where are we currently? Currently in steel industry, there are tough conditions. So extreme temperatures, noise, heavy machinery, but one threat comes very silently, and that's carbon monoxide, CO. So carbon monoxide mainly is a result from combustion process of carbons where the oxygen level hasn't been sufficient. And it is highly relevant because carbon monoxide is, for example, part of the blast furnace gas. Yeah, so it's a dangerous substance. And let me show you some details why. So the main problem is that it comes very silently. It's colorless, it's odorless, so you can't rely on your senses. Nevertheless, it's toxic and highly flammable, and that's really a bad combination. You will be well aware of it, and most of the steel producing companies are using gas detection devices to detect those hazardous atmospheres and to react on it. It's not only CO, there are other relevant gases in steel industries like CO2, like SO2, so different challenges here. But the main part is carbon monoxide. So one example, at ArcelorMittal in Germany, we have about 300 fixed gas detector installed in the plant, and 95% of them are measuring CO. But there's another gas raising up in the relevance in steel industries, and that's hydrogen. And here we come to the topic of the transformation in steel industry. So there is a high demand on green steel. And so the CO2 has to be decreased dramatically, and hydrogen seems to be a very suitable solution on this pathway to zero emissions. So one example is Salzgitter AG, a company from Germany, a steel producer, and they have a very ambitious project currently. It's called Salcus, and here it's one part is the production of green hydrogen, and the second part is the usage of hydrogen in the direct reduction process. We will come to that example later on. But, and that's here we come again to the challenge. So hydrogen is a very explosive gas, and there are some topics about hydrogen you have to be aware of. And so the main threat is the explosiveness of this gas. And related to this, we have a lot of topics about suitable equipment that must be certified. We are talking about X areas and the classification. And also standards and regulation will get stricter and stricter. That at least is what we currently see on the market. And this is now the part where I would like to hand over to Marcus, and then we will come back to more insight regarding explosive atmospheres. Your stage, Marcus.
Yeah, thank you, Ollie. Yeah, thank you very much for your introduction, also about giving me guidance to my topic, speaking about explosion protection. So we heard about the risk in your industry, about gases which are toxic on the one side, but on the others, also you're facing with substances which can create an explosive atmosphere. And my presentation consists of 4 chapters. So I will speak about the standards, which you could use as a guidance, or you know already. We have to speak about classification of areas, the selection of detectors, and we have to speak also about performance. Yeah, so it means if you want to detect something, you want to have it with some accuracy, with some reliability, because we are talking about safety, and we can't use, I would say, equipment from the supermarket or from the do-it-yourself workshop. So we have certain requirements, and we will come to this. Okay, so we heard already that you have a transition in your industry going from, I would say, existing gases, and also like having a new, which is hydrogen, which will change your safety and risk analysis. And before we step into this, let's have a look about what hydrogen means. And hydrogen, we have to know, if you're not familiar with, but it's the smallest existing molecule. Yeah, it's flammable, it's not toxic and not corrosive. So in some cases, especially non-toxic, non-corrosive, very good for workplace atmosphere. Flammable is not so nice. It's colored, so we can't smell it, we can't see it. And as I said, the small molecule and the lightest gas. So the density leads to the effect that it will always go up. And as also Oliver said, it's very extremely flammable. So it can easily form an explosive atmosphere with air and needs very few energy to ignite. So if we compare this to an, I would say, conventional gas, which most of people know, which is methane, and we compare then the parameters, so like density, then you can see that hydrogen is a tenth compared to methane, so it's much lighter. If you look for the ignition temperature, so what is the temperature you need to burn it, it's very similar. Also about low explosion limits. So it means at which point you have an explosive atmosphere, which in combination with an ignition source will lead to an explosion. But what differs already is the upper, that means the range to where the gas is dangerous, so can form an explosive atmosphere. So we see 77 compared to 14 volume percent. But the highest risk is the amount of energy we need to ignite it. And there we see is in terms of what we are used to methane. So only 0.02 millijoule are needed to ignite hydrogen. So very, very few energy. That leads to the effect that equipment which should be used in this area need a marking or a certification for air to or including to yeah, this is compared to methane, so 2 classes higher. So it means if you have already gas detection in place and you have safety measures, you have to rethink these. So you have to redo your risk analysis, because the gas has different property, how it expands and moves in the when it's released, and you have to consider other equipment regarding the classification. This one is about standards. There are many lines here. We have standards, guidance, give you the possibility to find a way to deal with risk. We have in Europe harmonized standards, and button-wise these are also harmonized with the ISC. So in the world, standards are all harmonized. We have only different versions, variants of the real estate, but the content is mostly the same. And when we speak about, we have two sides. On one side, we have the entry, you as a company, using or dealing with production. And on the other side, we have manufacturer like Draeger, who supplies manufactured devices which can be used in explosive atmosphere. And I highlight now 3 standards which are relevant. And the first is, if we speak about explosive gas atmosphere, we need to classify the areas so that we know how high is the risk, what is the probability that an explosive atmosphere can raise there or can be present. And there is the ISCEN 60079-10-1 for gases. Another one which we will also cover in this presentation is the ISCEN 60079-29-2. This is about gas detector, means selection, installation, use, and maintenance of detectors for flammable gases and oxygen. If you have guidance on how to select, I think we need also a standard which defines the performance. So to define criteria for detectors which can be used and should be linked to the selection process. So these are, I would say, 3 relevant standards, and we will, in my presentation, we will later see on or hear what is the content and the meaning of these. Okay, so we want to do explosion protection, and what we always do there is we speak about primary explosion protection. So the idea is always the first, we want to prevent explosive atmosphere. Or put it the other way around, you're dealing with substances which can form up an explosive atmosphere, but maybe there are possibilities to prevent that they reach a level that there is an explosive atmosphere. And this can be achieved by designing your processes or your equipment that they are gas tight, so the probability is very low that you will have a leak. Or you use ventilation, so you remove gases out of the application, or you use detection to pick these up to activate measures to keep the area free of explosive atmosphere. So this is the primary. So we want to prevent the formation of explosive atmosphere. The second, so if we can't avoid this because it's part of the process that explosive atmosphere could be present, then at least we have to prevent that ignition sources are present. So equipment which could ignite our explosive atmosphere. And for this, we use X-certified equipment only. So when we define and have identified the probability of an explosive atmosphere and have defined what are the requirements for the equipment, we can select the right equipment which can be used there. And as well, we have to secure that electric installation, grounding, etc. is properly. If this is all done, but nevertheless, there could be always the risk that you still have an explosion, then the third level is what we call the constructive measures. So we design our application, our processes that the propagation is reduced. So the effect of a explosion is limited. Yeah. So using materials which are fire retardant or fireproof, you use pressure release valves, or breakthroughs in the walls so that the pressure is released so that we don't have a collapse of the building. For our presentation of today, it's important we will concentrate on the primary pillar here. So we want to prevent, and as we speak about gas detection, the good message is here. I can't use the pointer.
Sorry. Oops.
So the good conclusion on the first step is you can use gas detection, as I said, so we can detect a possible explosive atmosphere, and gas detection itself is a measure to secure primary explosion protection, how we will see on the following slides. Yeah. So just to concentrate again on the primary explosion protection measures. So on the one side, we have to look on the formation inside an machine and apparatus, so where we have an enclosed environment, and there we can easily measure the concentration and keep the concentration below the explosion limits. In cases where we have high concentration, we can use inert gases, so we reduce the oxygen level inside so that the third element to achieve an explosion is not present. But if you go this way, you need sensors to control the oxygen level inside your process. If we want to concentrate on the outside of the equipment or the plants, so then we speak about explosive atmosphere in the vicinity of plants or parts of the plants, then reduce, we have the possibility by the design, as mentioned before, so have a tightness installation, and there we have different levels of tightness. It can be constructive and it's durable, so it means we can be sure that it will not leak to the outside, but most installation we have to consider pumps, valves. They are only tight in combination with organizational measures, and this could be by frequent inspection by using a portable gas detector to control the atmosphere, or you use a stationary gas detection system which is installed there and is permanently observing the atmosphere. If we have installation inside in a building, then we can use ventilation, for example, to dilute the concentration. So by constantly adding fresh air to reduce the concentration of our flammable substance and keep this on a level below below the lower explosion limit. So by this, we dilute and we prevent or limit the explosive atmosphere. Important to know is this is only necessary when we, I would say, expect quantities of a gas or vapor that special protective measures are required. Yeah, so if we have a cylinder filled with hydrogen, for example, and the quantity of the cylinder is as much, and if this would leaking in a closed room, then we need to consider, is the quantity of explosive atmosphere so high that you will have, in case of an explosion, a damage to persons or to the building, then we are on a level which is dangerous. But if this would be stored outside and this would be released and diluted by fresh air, then there is not the risk that we have, I would say, high quantities. And then in this cases, the standards, which is the EN 1127, defines an area in which an explosive atmosphere is not to be expected in such quantities that special protective measures are required. It's considered a non-hazardous area. So it means we have nothing to do. We need to document, we need to consider this our risk analysis, but we are done. In all other cases, we have to consider this and go for the next step. If we are looking now for gas detection, so if we want to use gas detection system for our primary explosion protection, then there are three types of gas detection systems. The first is just with a warning function. That means we have somewhere a sounder and a light which is activated in the case, and the operator needs to take measures. So by having working instructions that people have to leave or they have to switch manually valves. So this is just a warning. The second step is using automatic switch functions. That means the control system will activate ventilation or will close any kind of the process, but the process itself will stay in operation. And the last is what we call emergency functions. So in this case, the process will be shut off and only systems which are relevant for the emergency and to keep a safe state are kept in operation. So we see a gas detection system can have a big impact to your process, but also to your safety. How do we know how high the risk is or where to place a detector? We need to classify the area. We need to identify the risk. And besides the what you did in your risk analysis to identify that you have an explosive or a gas which can lead to an explosive atmosphere, we need to define the properties of it. And this is done in the classification. And for this, we have the ICEN standard 60079-10-1, which is a good guidance to run through. And interesting is there's a separate chapter about hydrogen, so special measures which should be considered when you do or you deal with hydrogen in your application. One of the things, time is too short to give you a complete run through this standard, but first thing is we need to consider the forms of the release. As hydrogen can be in different physical states. It could be a gas, it could be compressed, it could be an liquid. So if we speak, for example, about electrolyzers, then when this is leaking, depending if it's a normal pressure, it could be just a hydrogen as a liquid leaking out and then vaporizing. If you have a high pressure electrolyzer, it will be compressed gas. So you will have different form of release of your hydrogen, and this needs to be considered on your measures. Yeah, and so if, for example, you have ventilation, or your building is in an open design, you will have always the effect that the air which is coming into your room will either distribute, or with the air movement, at least it will dilute your explosive gas. So we have two basic functions we want to achieve with the ventilation. The one is we want to increase with the dilution by adding or by moving the air. We want to dilute and bring down the concentration of the explosive atmosphere, and we want to avoid that the explosive gas is expanding in your plant or in the area. So we want to limit the extension. The other is by using ventilation, you can classify an area as a zone. And if the ventilation is an active measure, you can also declassify or bring it to a lower level. So instead of having a zone 1, you have a zone 2. Or if your ventilation is perfect, you can also bring it to a non-zone. Important is always you need to consider how the air movement is inside, and if you have blockages or any kind of obstacles which could avoid that the gas release, what we are faced with, has no chance to escape, or we can't detect it. So important is to consider what are possible air movements, air streams, ventilation, all these, as this has a direct impact how our explosive atmosphere or gas will vaporize in the room. Important is also to consider if you are talking about liquids, vapor. So if you increase the ventilation rate here, so with a higher airstream, you will also increase the evaporation of your liquid. So your liquid has the evaporation always depends on the temperature of, or what we call the flash point of a substance. So depending on the flash point and the pressure, the liquid will vaporize. You will have a vapor, but this vapor will be blown away by your ventilation. And if you increase the ventilation rate, the vapor has a chance to build up much faster. Here's an example from a handbook to give guidance on how to design applications, and by using different measures on primary explosion to protection, and what is the resulting zone in this application. This is a compressor stage, which is designed durable, technically tight. So we expect under normal operation, it will not leak. So all connections are tight. But additionally, as this is an inside a building, there are natural ventilation. So we use the effect that temperature difference from outside to inside leads to the effect that we will have always an air movement to the room. And if this construction would be leaking, this would be immediately taken away. This is especially, or the leading zone is 0, so no zone, as we don't depend on any kind of control system in this. So depending on how reliable your system is, it will also has an impact on how you design or how is the resulting zone. Nice to know, or nice effect is if your resulting zone is in no zone, you don't need to use, for example, a drive which is explosion protected, or light which is explosion protected, because as your design of your measures always secure that no explosive atmosphere can build up, there is no necessity to select X-certified equipment. So it's a very interesting collection of different typical installations in the industry, and which measures can, or what the impact of the measures is in the resulting zone. I mentioned that there is an appendix about hydrogen. Also in the beginning, we talked about that the ignition temperature of hydrogen is 5 or close to methane. So if you're using methane or propane, you know what are the temperature impacts of your equipment, so that hot surface will not ignite a possible leak. But what is different is what we learned is that hydrogen has a different density, so it is a lightest gas. It will raise up immediately, and what you could have if it's in a closed area, could have an accumulation of your gas in overhead spaces, and especially if you have a closed roof and areas which are not very good ventilated, the gas will collect there. So it will stay there because there's no air exchange. So that means if you know already from the design of your building or your plant, you need to consider possible areas and also how you want to secure that you have correct ventilation, or by adding separate windows to the roof, which you can activate, for example, when you place a detector close there, controlling all the time the gas concentration. Also important is, for example, when you have hydrogen as compressed gas and this is released, you will have a jet which goes first straight out of the leak, but due to the density, it will very fast go up. So this is it's different when you have other gases, which like CO will collect on the ground. And this leads then to the point 8 in these appendix about the positioning, as mentioned before. So depending if we have just a normal room where we have a leakage, the gas will go up and we should position a detector close or higher than the expected point of release. When we have ventilation in between, then the detection should be very close to the area where we want to have the exhaust or where we have the release point to the outside, because there's the highest airstream. So the probability here is highest that the detector can pick up the gas. For gas detection, it's always important, especially on this kind of technologies, the gas needs to reach the detector. So if by the ventilation, the gas molecules are moving a different way, the detector has no chance to pick up the concentration, or the concentration which is indicated could be very low and not represent the actual situation. When you position detectors, you need also to consider that they need maintenance. You need from time to time to check, to calibrate these. So the positioning should be also in a way that you consider the work of your maintenance people. There are possibilities either positioning using equipment to, for example, we offer a remote calibration adapter so that you still have a point detector under the roof, but by using accessories, you can apply the test gas concentration or calibrate the sensor from the ground. Yeah, but this needs to be considered during your design phase. Coming to the third part of my presentation, this is about how to select the detectors, because we want to detect flammable gases and especially now hydrogen. There's a standard which is in the 79-29-2. This is about the selection, and right in the beginning we see a scope of this, and in the scope is that the requirement for using gas detection is that these needs to be comply with the 29-1 and 29-4. So 29-1 is for point detection, 29-4 is for line of sight. So that means if you follow this guidance and use this for primary explosion protection, the equipment which is selected based on this should be compliant with these performance standards. We come in the next chapter to this performance. What kind of technologies, sensors can we use based on these standards? This is on the first. We concentrate on the flammable gases here. So we always try to be below the explosion limit. So there's catalytic bead sensors, infrared, semiconductor, electrochemical, FID, PID. So these are typical sensors which can be used for flammable gases. But if we want to detect hydrogen, and we come later to the sensors itself, we can only concentrate mostly on two sensor technologies. This is catalytic sensors, and this is the electrochemical sensors. You can also use FID or PID, but this is, I would say, not typical for the primary explosion protection. What is important to know is if there are new technologies stepping into the market, like ultrasonic leak detection, IR cameras, and etc., you can use this, but only as supplementary. So this can't as your, I would say, your safety concept is based on certain detectors, like here, you can't replace this with the alternative, but you can add, for example, ultrasonic gas leak detector, for example, to reduce the amount either, or to have a higher reliability of your system. Let's have a look to two principles for gas detection. One is electrochemical sensors. Here's a schematic on this. So what we have is the molecules vaporize through a membrane into the sensor. You can compare this like a battery. You have electrodes, you have an electrolyte. On the electrode, on the one, you will have a chemical reaction. You will generate electrons. And if you have a circuit around, then you can measure this amount of electrons and you get an indication. Important on this is, and this is shown here by the chemical reaction below, as example with CO. So what always happens is the gas is coming into or vaporized into the sensor, and you will have always a liquid. In this case, it's the water inside, always combined with an acid or with salt. And we will have a reaction of the CO with the water, forming CO2. And important what we see is we create the electrons. And on the counter electrode, we have the opposite reaction, that the electrons are recombining with the oxygen. So we have a closed process. What the sensor is measuring, it's not measuring the CO or O2, it's measuring the electrons. So what we do is we generate electrons, and this is a proportional indication of the gas which is oxidizing or reducted. So that means our measures is not the gas itself, it's a part of the process. So, and that leads to the effect that you could have a similar reaction also with other gases, and that's the reason why sensors have cross sensitivities, because a similar gas can lead to a similar reaction, creating electrons which we measure. So electrochemical sensors are always, I would say, not selective. I would say you can limit the amount of impact of the cross sensitivity, but to the chemistry, it's always, as we measure a production product like the electron, you have always the impact or interference with other substances. And interesting is this can have a positive or negative impact. That means you get a higher reading or lower reading. So the other gas can add your signal. So instead of 100 ppm, you measure 120, but it can also reduce, because you can have also an opposite reaction here inside. Important is also, as we can see here from the formula, we need always oxygen. So a measurement with an EC sensor without oxygen is not possible, because otherwise the process will stop here, and the chemical reaction will not generate any kind of electrons, so we get no reading. I mentioned also we have here some water inside, so liquid. So we need a certain environmental condition for the sensors that it can operate. So if we need, what we typically specify is 5 to 10% relative humidity as a minimum. Otherwise, the humidity from the inside will vaporize to the outside, so the sensor will dry out, and the electrons can't be generated or can't move through the electrolyte because there's nothing left. So you see, electrochemistry is quite simple from the idea behind, but you have physical or environmental effects which can influence the performance of your sensor. So you need to keep in mind how and where you want to use these sensors. The other principle, how we can detect gases as catalytic bead or catalytic sensor. We have again our gas molecules which vaporize, in this case, through a flame arrestor. We have an active, I would say, a hot wire. And what we do is an oxidation, so a reduction of the, in this case, methane in this example, could be also hydrogen with oxygen. We generate CO2, water, and one of the part is we have a heat of reaction. So we add energy, but as part of the combustion, we get additional energy. So the heat of reaction leads to an increase of the temperature of this wire here, and this temperature increase is our measure, our direct proportional measure for the amount of gases which are inside. As you can see again, we have an indirect measurement. That means we are not measuring directly gas molecules, we measure the amount of energy which is generated. So that means we are not really selective. We can be, I would say, partially selective by selecting the sensitivity or the heat of the ballistas, but nevertheless, it's not very selective. As we have here in combustion process, we need to secure that this combustion is limited to the sensor. So that's, for example, the sensor typically designed as a flame-proof or explosion-proof enclosure with a flame arrestor in front. As like the EC sensors, we need always oxygen, otherwise we have no combustion. Geht wieder nicht. Sorry, again. Okay, so as mentioned, we have always the oxidation process with our gases, and mostly it's hydrocarbons, but we can also detect by this hydrogen. And depending on the molecule structure, we get different signals, so which are related then to the thermal reaction. So, and when you use sensors like this, the best and safe way is always to calibrate, to adjust the sensor to the substance with the lowest sensitivity you are expecting to have always the correct signal on your side. Important is also to know that these catalytic bead sensors are only or can only operate below the low explosion limit, because here you still have a mixture with the oxygen and the flammable gas, which can be combusted and give you a linear response. And in the moment you are crossing the lower explosion limit, the curve, the signal what you will get is not linear going up, it will go down, because then we have the situation that the amount of oxygen is not sufficient anymore for this process to give you a linear reading, so that the sensors for this type are always limited to just low explosion limit. And we need minimum 10 volume% of oxygen so that we still can create this combustion process. So in sensors, here's also mentioned the standard needs to comply. So the sensors are tested according to the standards, how linear, how reliable is their signal. We come in the last chapter to this in detail. So just very fast to summarize. So what is your checklist when you think about combustible gas detectors? We need to know what kind of flammable gases or vapors in which concentration are present, because this defines which technologies you can use. Are there other gases or vapors present because you have cross sensitivities, or maybe you need also to select the different calibration? We need always oxygen and a sufficient amount, and not oxygen enriched atmosphere, because this leads to other effects. What is the measuring range? So it means what concentration the device should indicate. Response time, for example, because these principles, a catalytic bead sensor can take up to 30 seconds before you get your alarm. So you need to consider this if you have any kind of measures which should be activated. We need to consider ambient conditions, temperature, pressure, etc., but also the atmosphere around. Dust, poisoning substances, etc., have an impact to selecting the right sensor, but also maybe to use accessories to protect the sensor itself. Coming to my last part of the presentation, this is about performance. As I said, if you select equipment, and this is also written in the standards, we need to use reliable equipment. And how you can identify this, or what is the performance approval looking at? So we have two elements. On the one side, we have the detector in the field, in the hazardous area, and we have our control system. So on the one side, we have the requirement for explosion protection. So the device needs to be certified and tested accordingly. And you find this by the marking on the device or by your examination certificate, that this is then accordingly stated there, that the detector, for example, can be used in the zone 1 here for gas atmosphere. If you use the sensors here for primary explosion protection, so that you measure gas concentration and you have a control system which activates, for example, any kind of switching of a ventilation or also for emergency shutdown, then the control system has also a big impact to your complete system here. And that is a requirement if we talk about primary explosion protection for the 29-1, that not only the detector is tested and approved, but also your control system, because you need to secure that the signals what the sensor is providing is correctly understood and interpreted by the control system. And what you will find then, if this control system, what we call is a kind of associated equipment, can be connected to a device in the field, but is not intended to be used in a hazardous area, you will find, especially in Europe, a marking on it that indicates that it can be or is allowed to be connected to a device in explosive atmosphere, but is not intended to be installed there. So you will find these in the ATEX world, we have round brackets. If you look to the ISC, you will see square brackets, because the interface here is interfering with the device in the field and is also interfering with your measures. So, and if a device is approved, certified by a notified body, by for the ISC or the N, you will get a kind of test report in combination with the certificate. In this case, I took the sample from the DECRA for one of our products. You will find on the report the different products which have been tested by the notified body. So which standards were with the scope, and here we talk about measuring performance, and also which date, because when we look about standards, they have always a release date, and a certain time you will find an update, and then you need to apply for an update of your certificate. But it's not only sufficient to have the standard on the listed on your certificate. It's also about, because we want to measure certain substances as primary explosion protection, and then it's important that the gas which you want to detect is as well part of the certificate. In this case, it's hydrogen. So if we want to use gas detectors for hydrogen detection, then I could only recommend to have a closer look to the certificates of the devices if hydrogen was also tested by the notified body. Yeah, this was very short an overview step into gas detection, primary explosion protection, what are requirements. And I would like to hand over to my colleague again so that we can speak about best practice.
Okay, thank you. Thank you, Marcus. Great insights here on the topic. And if you now have the feeling that there's quite some complexity in this topic to ensure plant safety, don't worry. There are experts like Draeger who, of course, would like to support you on your way. And that's leading us to the last couple of slides for today, because I would like to show one example, one reference case we recently have together with the company. We started for a couple of minutes, and that's Salzgitter Flachstahl AG in Germany. And as I said, there is a project phase regarding hydrogen, green hydrogen production, and direct injection. And the positive part is that we came in this project in a very early phase. So not at a moment where a quote is needed, but also in the phase where the risk assessment has to be done. And there we were more than happy to bring in our expertise on this topic, but at the same time learn about this very important application where a lot of steel companies are in. So what we did a holistic safety approach, safety workshops on it, and we came to the point that in the end we need three important elements. So first of all, we need to detect H2 in the hull of the electrolyzer and detect it in LEL range, so lower explosion range. So then additionally, we need some H2 detection in the electrolyzer on a low level of concentration. So it's a ppm range to detect, for example, leakages in a very early phase. And last but not least, there's the need to monitor oxygen, because there is some nitrogen involved in this technology, and here it has to we have to make sure that there's no oxygen deficiency as threat for the workers. And of course, all in the framework with maintenance, training, and service, because knowledge is key, and that's leading us now to the end, the right keyword, knowledge, and we really hope that we could bring some good insights here today to you. Okay. Now, one of our last points, we would highly appreciate to stay in contact with you, and that's why you will find here the QR codes directly linked to our LinkedIn profile. So if you want to address some topics afterwards to us directly, please choose this QR code. And before we come to your questions, I would like to give you a short outlook because there's more to come. The next session will be focusing on confined spaces in the 4th of July. Then we will have a deep dive into the special risks in maintenance work. And then we will get a bit more operational about the right usage and maintenance of mobile gas detection devices. So stay tuned, there's more to come. And all sessions, as you might already know, are recorded or will be recorded. So there will always be the chance to have a look on it at a later point. Okay, so that's all from us for the moment. Thank you for your attention. And then I would like to hand over back to Andrew. Yeah, let's start the FAQ session, Andrew.
Thank you, Oliver. Thank you, Marcus, for, I think, an excellent presentation. You touched on some of the real key topics around hydrogen in particular, and I certainly learned a lot about how sensors work, which I was largely ignorant of up till now. I saw them rather as a black box. So thank you for that. We do have a number of questions, which hopefully we can take some time to run through, and maybe I'll start at the top. You talked about in your presentation around positioning sensors, and it's important to put them in the right place. How can somebody who's wanting to use gas sensors ensure that they're correctly locating them?
Okay, so when the risk analysis is done, so you know about which gases could be present there or will be present, so so that you consider or you know their properties, so like density, flashpoint, etc. And you have selected the right detector so that they're capable. You need to think first about, is the gas heavier or lighter as air, and in which form the gas will be released, or the vapor. So that means, will it directly go up or go down, or it will take some time? But also in your design that you have present, have you a natural ventilation so that the gas could be distributed, and this needs to be considered. So there are two ways how you can, I would say, step in. The one is there are tools like gas mapping where you can simulate these. So you can set up, you can upload your the design of your plant, and then by using the information of the gases, you can simulate this. This is, I would say, the very accurate but work-intensive way. But this would be the, I would say, absolute correct way, and there are companies offering this. Another possibility is to get an idea. There are equipment what you can use which generates steam. Yeah, so just to get a first idea where the ventilate, or if you have ventilation in this application, and to simulate and to make it visible so that you have an idea where the possible gas release will go in which direction. So this gives you the possibility when you have you're in the design or installation phase to select where's the best place to install. Another possibility is request experts like Oliver mentioned, or there are third parties which offer the services to confirm this. Yeah, I hope this was sufficient as answer.
Thank you. These detectors often form critical protection, part of our critical protection system. To what degree do users need to think about redundancy? Is this generally built into the sensors, or is there need to design that into the protection system when they're put into place?
Yeah, so I would say we have, besides the performance of equipment, we have also the topic, what is the reliability, which is what we call functional safety. So people who are used with machinery know this already for a long time. Now this is also relevant for safety. So functional safety, so how reliable is your equipment, but not only your equipment, the complete chain that you build up from detecting, controlling, and implementing measures. So all equipment, or most of the equipment that you can get from the market from today, they have at least a classification, what we call SIL, safety integrity level, which give you an indication how reliable this is. So, but in parallel, you need to know what is your requirement on reliability. So in the process world, you normally have what we process liability factor, and the symbols would be 0, so you have no requirement. But if you have, for example, a high requirement would be factor 3, and you want to get it on from 3 to a low level, then you need to think about how many steps you want to go down, and based on this, you select the equipment. So this is, I would say, a separate engineering requirement beside positioning to design, I would say, the reliability of your control or measuring system. But this is already present today, and this gives you the idea, okay, how can I reduce the risk? Is one detector sufficient, or do I need a second for redundancy? So this is part of this analysis.
Excellent, thank you. I guess thresholds come up as another issue. Do the sensors come with a fixed threshold to be alarmed, or is that something that user really needs to think about as they look to build their protection system?
Yeah. So if we talk about toxic gases or about oxygen, then we have thresholds which are defined by national regulations, and these are implemented in the sensors or the transmitter. You can change or select. If we speak about flammable gases, we have default settings, but this is not considering the idea how you want to use the detector. So that means if, for example, you just want to warn, then you need an early warning, so low levels that the worker has a chance to act. If you have, for example, automatically a ventilation system connected to you, so then you have a kind of control loop. For example, you can use higher levels because you need a certain point where you want to act, but you have also a point threshold where you will stop the process because your measure is not effective. So typical low explosion limits, it's either by 20% or so for flammable gases. But you will find also application where 40% is used because there's enough, I would say, time to react on before you get in an explosive atmosphere. So it's also part of your, I would say, it's always, you start with the risk analysis, and this gives the idea how fast you need to react or what kind of reliability your system needs. So, and based on this, you select the equipment and set up, I would say, the requirements of your thresholds. It's just a control loop what you build up.
Thank you. Our members are clearly all around the world. I noticed a number of the standards you showed us were largely European. Would those standards be applicable to folks, operating in Asia or in other regions, or would there be more specific national or local standards that they need to look at in their own applications?
Yeah, I put it that way. So the good thing with the ISC is it's worldwide. So mostly all relevant countries are member of the ISC group. And over the decades of years, this has now also US is member of the ISC. So also UL is following the standards, also Brazil. So there's always a chance. There are also sometimes national regulation for some industries, but in general, I would say these standards are mostly applicable for the complete world. The only difference could be different thresholds, different release versions of this standard, so or some national special requirements. Yeah, so for example, in Germany we have additional high requirements on certain gases or substances, but this is then just on top. But as a first guidance, these standards you can use all over the world.
Fantastic. Thank you, Marcus. We're just running out of time, I think, or the time we've had allocated. There was maybe a fairly specific question came into the Q&A for Alejandro, and maybe we'll look to pass that to you directly after the webinar, so you can answer that. As we said, the recording, the webinar has been recorded. It will be repackaged as a course, which is freely available via our Steel University website with copies of the slides and the recording of the presentation. So that may take a few days to get that online, but you should hear about that if you've registered very soon. So I think we will close things out at this point. Once again, I would like to very much thank the Draeger team, Oliver and Marcus, for their fantastic presentation and their expertise. We will be doing this again, as Oliver pointed out, next month, when we talk about a different aspect of this critical issue of gases and asphyxiation within the industry. So I'm really looking forward to talking to you guys again next month. And
thank you.
We will
join you then.
See you all again.
Thank you, everybody who's participated in our discussion today, and we look forward to our next session.